Stand outside on a clear night and look up. The sky stretches endlessly above you, scattered with pinpricks of light that seem impossibly distant. Now look around. The ground beneath your feet feels solid, infinite in every direction. Mountains rise to touch the clouds. Oceans span horizons you'll never reach. The earth, your earth, feels vast, eternal, central to everything. This feeling isn't wrong. It's human. It's the only perspective evolution equipped you with. For nearly all of human history, we were the center of everything. The sun rose for us. The stars wheeled around us. The ground
But
stood
that's not
still
all.
while the
Something
heavens
out
moved.
there in the
This
interstellar
wasn't
darkness
ignorance.
has been
It was
following our
honest
probe for
observation.
years.
From where you
Something
stand,
watching
the
us.
Earth genuinely
Something that
feels
just
like the
decided
stage
to make
upon which the
contact.
universe performs.
To understand this mystery,
Even
we
today,
need to go
knowing
back to
better doesn't change
1977.
the instinct.
Humanity
You wake up
made
in a city
an
of millions, drive past endless suburbs, fly over continent-spanning farmland. You see photographs of Earth from space, that delicate blue marble, and it still looks enormous. 7 billion people, 197 million square miles of surface, oceans that could swallow entire nations. How could something so vast be small? But here's the problem. Human brains are spectacularly bad at understanding large numbers. We evolved to count prey animals and rival tribes, not to grasp the difference between a million and a billion, let alone a trillion. When someone says the universe is big, you nod. You've heard it before. The number washes over you, meaningless, leaving no mark. A billion seconds ago, it was 1993. A trillion seconds ago, humans hadn't invented agriculture. See? Even that doesn't quite land, does it? This is the gap we need to bridge, the chasm between what you feel standing on this apparently infinite Earth and what actually is. Because the truth isn't just that we're small, it's that we're incomprehensibly, almost insultingly small. The kind of small that breaks your intuition. The kind of small that makes you question whether the word small even carries enough weight. So, let me ask you directly, how small are we, really? Not in terms of numbers you'll forget. In terms of scale you can actually grasp. Let's start with the only home humanity has ever known. Earth measures roughly 12,742 kilometers across, about 7,918 miles if you prefer. Drive a car at highway speed without stopping, and you'd circle the equator in about 17 days. Fly it in a jet, and you'd manage the same trip in under 2 days. On foot, walking every single day, you might circumnavigate the planet in a year or two if you somehow cross the oceans. See? Still feels massive. But here's what we miss. All of human civilization, every city, every farm, every road, every person who has ever lived, exists on the outermost skin of this sphere. We occupy the surface, not the interior, not the depths, just the thin, fragile boundary between rock and sky. The Earth's crust, where we've managed to dig our deepest mines and drill our deepest wells, extends down perhaps 30 to 50 kilometers. Beneath that lies the mantle, the outer core, the inner core, thousands of kilometers of material we've never touched and never will. We live on a rind. We've scratched perhaps 0.2% of the way to the center. Now consider the atmosphere, the ocean of air that makes life possible. It feels vast when you're standing in it. Weather systems span continents. Clouds tower kilometers high. Airplanes cruise at 10,000 meters, and you're still unmistakably in the atmosphere. But pull back. See Earth from space, and the atmosphere becomes a wispy blue halo, a thin veil clinging desperately to the planet's surface. 99% of it is contained within just 30 kilometers of the ground. If Earth were an apple, the atmosphere would be thinner than the peel. If Earth were a basketball, the breathable air would be thinner than a sheet of paper wrapped around it. This is the fragility we rarely acknowledge. Our infinite sky is a film. Our vast oceans average less than 4 kilometers deep on a planet that's over 12,000 kilometers wide. Mount Everest, that monument to Earth's grandeur, rises 8.8 kilometers, barely a wrinkle on the surface, proportionally smaller than the bumps on an orange. Every empire that has ever risen, every war ever fought, every species that has evolved, every glacier that has carved a valley, all of it happened in this vanishingly thin shell. Why does Earth feel so big? Because you're inside it. You're embedded in the surface layer, crawling across it at human speed. From your perspective, the distances are genuinely vast. It would take you a lifetime to walk across Asia. The Pacific Ocean is genuinely uncrossable on foot. But zoom out even slightly, not to the stars, just to the moon, and Earth becomes a small, delicate sphere, mostly empty inside, wrapped in a membrane of water and air, so thin it's almost negligible. And this is still just Earth. We haven't left home yet. This small, thin-shelled world, this apple with its paper-thin atmosphere, is about to get smaller, much smaller, because now we're going to step away from it. Look up at the moon. It seems close, doesn't it? A companion, Earth's faithful satellite, hovering just overhead. In photographs, especially those showing Earth and Moon together, they often appear as neighbors, two celestial bodies sharing the frame, practically touching. Those pictures lie. The Moon orbits Earth at an average distance of 384,400 kilometers, roughly 238,855 miles. That's about 30 times Earth's diameter. 30 Earths, lined up edge to edge, would fit in the gap between us and our closest celestial neighbor. Try to picture that. You can't, really. 30 Earths is already beyond intuitive grasp. So let's try something more visceral. If you drove to the moon at highway speed, say 100 kilometers per hour, the trip would take you 160 days of continuous driving, 4 months without stopping for sleep, food, or fuel. Fly there in a commercial jet at 900 km/h, and you'd still spend nearly 18 days in transit. Even the Apollo astronauts riding the most powerful rockets humanity had ever built needed 3 days to cover the distance, 3 days, to reach the nearest object in space. Here's another way to understand it. Take every planet in our solar system, Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune, and line them up side by side. The total diameter of all 8 planets combined is roughly 380,000 kilometers. They would fit, with room to spare, in the empty space between Earth and Moon. Let that sink in. The entire procession of worlds from our solar system, gas giants and rocky planets alike, could be threaded through the gap we casually call Earth-Moon distance, and we'd still have space left over. Light itself, traveling at 300,000 kilometers per second, fast enough to circle Earth's equator 7 times in 1 second, takes 1.3 seconds to reach the moon. When you see the moon in the sky, you're seeing it as it was more than a second ago. Not much of a delay, perhaps, but it's the first hint of something critical. Space is not crowded. Space is overwhelmingly, incomprehensibly empty. This is the first scale shock. The moon, our familiar companion, the subject of poems and songs, the thing that feels close enough to touch on a clear night, is separated from us by a void so vast that every planet in our solar system could hide inside it. And the moon is our nearest neighbor. It's practically in our lap compared to what comes next. Because if this gap seems large, if 30 Earths lined up end to end feels impossible to visualize, then brace yourself. We're about to leave the moon behind and venture toward the sun. And the numbers are about to stop making sense entirely. Every diagram of the solar system you've ever seen is a comfortable lie. Textbooks show the sun on the left, planets strung out to the right in a tidy line, Mercury, Venus, Earth, Mars, and the gas giants beyond. They're all visible on the same page, neatly labeled, roughly to scale in size, if not distance. It creates an impression, the solar system as a neighborhood, a collection of worlds sharing the same street. The truth is nothing like this. Let's start with the sun. It's big. You know this already. but knowing and understanding are different things. The sun's diameter is roughly 1.4 million kilometers, about 109 times wider than Earth. If Earth were a marble, the sun would be a sphere 3.5 meters across, taller than a person, wider than a car. In volume, the sun could swallow over 1 million Earths, not 1,000, 1 million. Every ounce of matter in the solar system, every planet, moon, asteroid, comet, and grain of dust accounts for less than 0.2% of the total mass. The sun is 99.86% of everything. The solar system isn't a family of objects orbiting a star. It's a star with some rounding errors. Now let's talk about distance. Earth orbits the sun at an average of 150 million kilometers, a distance we call 1 astronomical unit, or AU. This is already absurd. Light from the sun, traveling at 300,000 km/s, takes 8 minutes and 20 seconds to reach us. When you feel sunlight on your skin, you're being warmed by light that left the sun's surface over 8 minutes ago. But here's where scale models fall apart. If you shrink the sun down to the size of a basketball sitting in the center of a football field, Earth becomes a grain of sand, not a marble, a grain of sand. And that grain wouldn't be sitting next to the basketball. It would be orbiting 26 meters away, nearly 30 yards from the sun, outside the football field entirely. Jupiter, the largest planet, would be a small p, roughly 135 meters from the basketball sun, more than a football field's length away. Neptune, the outermost major planet, would be over 780 meters distant. That's nearly half a mile. A tiny speck, invisible to the naked eye, orbiting a basketball half a mile away. And between these objects, nothing, void, emptiness. Those neat diagrams showing all the planets lined up, they never actually line up. Planets orbit at different speeds on different paths. Most of the time, they're scattered around the sun in seemingly random positions. If you stood on Mars and looked for Earth, you'd need a telescope, and you'd need to know exactly where to point it. This is what we miss when we think about the solar system, the space in space. We imagine planets as neighbors because we see them drawn that way, but the solar system is better understood as a handful of dust grains scattered across a stadium, with a basketball sun at the center, and everything else so far apart you'd struggle to find it. Even the asteroid belt, the crowded region between Mars and Jupiter that science fiction portrays as a dense obstacle course, is mostly empty. Space probes like Voyager and Pioneer flew straight through without bothering to navigate around asteroids, because the odds of randomly hitting one are essentially zero. The asteroids are separated by millions of kilometers. Emptiness, everywhere, emptiness. And we're still only talking about our immediate cosmic neighborhood. We haven't even left the solar system yet, because beyond Neptune, in the frozen dark where sunlight is barely a whisper, the solar system continues. The Kuiper Belt, the Oort cloud, regions so vast and empty they make the orbital distances we've discussed seem quaint. But we'll get there. First, we need to understand just how trapped we are in this tiny corner of space. Let's bring the planets down to human terms. You're standing in that stadium we mentioned, Sun as a basketball in the center, Earth as a grain of sand. Now look outward past Mars, another grain of sand but smaller, into the realm of the giants. Jupiter appears first, not a grain of sand, not even a marble, a grape. Jupiter is enormous. Its diameter is 11 times Earth's. Line up 11 Earths side by side, and you'd span Jupiter's equator. In volume, you could fit 1/300 Earths inside it, pack them in like oranges in a crate, and there'd still be room left over. In mass, Jupiter outweighs Earth by a factor of 318 times. Jupiter alone contains more mass than all the other planets combined, twice over, with room to spare. If the sun weren't there, Jupiter would be the gravitational tyrant of the solar system. Earth, by comparison, is gravitationally irrelevant. A rounding error. Saturn isn't much smaller, about 9 times Earth's diameter, 95 times its mass. If Jupiter is a grape, Saturn is a slightly smaller grape. Together, these two gas giants account for 92% of all planetary mass in the solar system. Earth, Venus, Mars, Mercury, Uranus, Neptune, and all the moons, asteroids, and debris combined make up the remaining 8%. We like to think of Earth as a planet, equal in category to Jupiter and Saturn. Technically true. Practically, it's like comparing a rowboat to an aircraft carrier and calling them both ships. Uranus and Neptune, the ice giants, are each about 4 times Earth's diameter and 15 to 17 times its mass. Even these distant, half-forgotten worlds dwarf us. If you placed Earth next to Neptune, Earth would look like a child's toy. But size and mass aren't just about bragging rights. They translate to power. Gravitational dominance, the ability to shape the solar system's architecture. Jupiter's gravity is so strong, it flings asteroids and comets around like toys. It acts as a cosmic shield, deflecting some potential impactors away from the inner solar system. It corrals the asteroid belt, preventing those rocks from ever coalescing into a planet. Its gravity tugs on everything nearby, influencing orbits across millions of kilometers. Earth's gravity? It holds the moon. Barely. If the moon were much larger or closer to the sun, Earth might lose it. We don't shape solar system dynamics. We don't protect other worlds. We don't bend the trajectories of passing objects unless they come very, very close. We exist, fragile and small, in a region the giants ignore. Here's the uncomfortable truth. If Earth vanished tomorrow, the solar system wouldn't notice. The sun would continue burning. Jupiter would continue its stately orbit. The asteroid belt would remain exactly where it is. No orbits would destabilize. No dynamics would shift. But if Jupiter disappeared, chaos. Orbits would change. The asteroid belt might collapse or scatter. Comets would fly in unpredicted directions. The entire architecture of the solar system depends on Jupiter's mass. We are passengers, not architects. And this comparison between Earth and the gas giants, is still within our own solar system. We're still comparing grains of sand to grapes, all of them dwarfed by that basketball sun at the center. Earth isn't just small in cosmic terms, it's small even by planetary standards. We're a minor rocky world in the inner system, outmassed by our neighbors. Gravitationally insignificant, clinging to a thin shell of air and water. And now we need to zoom out further. Because even Jupiter, that grape, that colossus, that gravitational king, is about to become invisible. Part 6. The edge of the solar system. We think of Neptune as the edge, the last stop before interstellar space. The final planet, orbiting 4.5 billion kilometers from the Sun, 30 times farther out than Earth. But Neptune isn't the edge. It's barely the beginning of the end. Beyond Neptune lies the Kuiper Belt, a vast ring of icy bodies and dwarf planets extending from roughly 30 AU to 50 AU from the Sun. This is where Pluto lives, not alone, but as one member of a scattered population of frozen worlds. Some are nearly Pluto's size, most are smaller, dark, ancient remnants from the solar system's formation. If our stadium model still holds, Sun as basketball, Earth as sand grain, 26 meters away, the Kuiper Belt would stretch from roughly 780 meters out to 1,300 meters. That's nearly a mile. And we're still not at the edge, because beyond the Kuiper Belt, the solar system doesn't end. It fades. The Oort cloud, a theoretical spherical shell of icy debris, extends from perhaps 2,000 AU out to 100,000 AU from the Sun. Let me translate that. From about 300 billion kilometers to 15 trillion kilometers. In our stadium model, the Oort cloud would stretch 26 kilometers out to 1,300 kilometers in all directions. That's not a football field anymore. That's the distance from New York to Miami. Earth would still be a grain of sand 26 meters from a basketball, But the solar system's true boundary would encompass multiple states. Light from the sun takes over a year to reach the inner Oort cloud, nearly 2 years to reach its outer edge. We live 8 light minutes from the sun and think of ourselves as distant from it. The Oort cloud is 2 light years away. Same solar system, same gravitational influence, unimaginably far. Now consider this. The fastest human-made objects ever launched are the Voyager probes, traveling at roughly 17 kilometers per second. Voyager 1, launched in 1977, has been flying outward for nearly 50 years. It's currently about 24 billion kilometers from the sun, roughly 160 AU. That sounds far. It is far. Voyager 1 has left the heliosphere, the bubble of solar wind that surrounds the sun. In some definitions, it's entered interstellar space, but it hasn't left the solar system. Not even close. Voyager 1 won't reach the inner edge of the Oort cloud for another 300 years. It won't exit the Oort cloud entirely for 30,000 years. 30,000 years. The furthest object humanity has ever built, flying away from the sun faster than anything we've ever made, will spend the next 30,000 years still technically inside our solar system's gravitational influence. This is the psychological shock. We haven't left home. Not really. We've barely stepped off the porch. Every human who has ever lived has existed within 0.001% of the solar system's true diameter. Every planet we've studied, every probe we've sent, all of it contained within a tiny bubble near the sun, surrounded by an incomprehensibly vast halo of frozen debris we'll likely never reach. And this entire structure, this football field turning into multiple states zone, is one solar system, one star's domain. There are hundreds of billions of stars in our galaxy alone, and the nearest one is still unimaginably far away. We've established that the solar system is vast, so large that our fastest spacecraft would spend 30,000 years just escaping it. Now comes the moment where comprehension truly collapses. How far is it to the nearest star? Proxima Centauri, the closest star to our sun, sits 424 light-years away. That's roughly 40 trillion kilometers, 40,000 kilometers, if you prefer to see the zeros. Light, traveling at 300,000 kilometers per second, takes 4 years and 3 months to cover that distance. Numbers this large are useless to intuition, so let's return to our models. Remember the stadium? Sun as a basketball, Earth as a grain of sand 26 meters away, solar system extending 1,300 kilometers in every direction? In that model, Proxima Centauri, the nearest star, would be another basketball located roughly 6,800 kilometers away. That's the distance from New York to London, across the Atlantic Ocean. That's how far you'd have to travel to find the next sun in our model. One basketball in New York, another basketball in London. Nothing but empty ocean between them. This is the structure of the galaxy, stars separated by abyssal gulfs of nothing, islands scattered across a dark sea so vast that even light takes years to cross between them. Let's talk about travel time. Voyager 1, humanity's fastest and most distant emissary, is traveling at about 17 km/s. At that speed, it would take approximately 75,000 years to reach Proxima Centauri, if it were pointed in that direction, which it's not. 75,000 years. Modern humans, anatomically modern Homo sapiens, have only existed for about 300,000 years. Civilization, agriculture, writing, all of recorded history spans maybe 10,000 years. A journey to the nearest star would take longer than all of human civilization has existed so far. Even wildly optimistic future propulsion systems don't help much. Suppose we build a spacecraft capable of reaching 10% the speed of light, a staggering engineering achievement requiring technology we don't remotely possess. That ship would still need 42 years to reach Proxima Centauri. The people who launched it would be elderly or dead by the time it arrived. Communication with Earth, an 8.5-year round trip for every message. We've arrived safely, 8.5 years later. Congratulations. This is why interstellar travel isn't just hard. It's a fundamentally different category of challenge than anything humanity has attempted. Going to the moon was difficult. Going to Mars will be extraordinarily difficult. But going to another star, that requires rethinking what a journey even means. Generation ships, suspended animation, self-replicating machines, or simply accepting that whoever leaves will never return and whoever sent them will never see the results. Here's the piece that truly breaks intuition. Stars aren't neighbors. They're not even distant neighbors. They're solitary lighthouses separated by oceans of void. Our galaxy contains somewhere between 200 and 400 billion stars. That sounds crowded. Billions of suns. Surely they must be packed together. No. The Milky Way spans roughly 100,000 light-years across. Those hundreds of billions of stars are scattered throughout a disk so large that even traveling at light speed, you'd need 100,000 years to cross it. Space is not crowded. Space is empty on a scale that makes the word empty seem inadequate. If you were standing on a planet orbiting Proxima Centauri and looked up at the night sky, you'd see stars. Thousands of them. The view wouldn't look dramatically different from Earth's night sky, but every single one of those stars would be light years away. Decades, centuries, millennia of travel time separating you from each glimmering point. The Sun itself, seen from Proxima Centauri, would be just another star. Visible, yes, probably fairly bright, but indistinguishable in a sky full of stars. Earth would be completely invisible, even with our best telescopes. A grain of sand, lost in the glare of a distant basketball. And Proxima Centauri is our nearest stellar neighbor. Most stars are hundreds or thousands of light years away. The stars you see when you look up at night, Sirius, Betelgeuse, Rigel, Vega, they're between 8 and 900 light years distant. You're seeing them not as they are, but as they were when their light began its journey toward Earth. We are not part of a stellar community. We are alone, isolated in the dark, separated from our nearest neighbor by a chasm so vast it renders the word distance almost meaningless. And this isolation, this loneliness, it's about to get worse. Step outside on a moonless night, far from city lights, and look up. If you're lucky, you'll see it. A faint, milky band of light stretching across the sky, as if someone spilled cream across the darkness. That band is your galaxy, seen from the inside. Edge on. The Milky Way is a barred, spiral galaxy, a vast rotating disk of stars, gas, dust, and darkness, measuring roughly 100,000 light-years from edge to edge. It contains somewhere between 200 and 400 billion stars. Some estimates push higher, each one a sun, many with their own planetary systems, scattered throughout a volume so immense that even light takes 100,000 years to cross it. Let's try to grasp this. If you shrank the sun to the size of a single grain of sand, the Milky Way would be roughly the size of North America. One grain of sand representing our sun, lost somewhere in the interior of a continent-sized volume of mostly empty space, with 200 billion other grains scattered throughout. The sun, and therefore Earth, our insignificant passenger, sits roughly 26,000 light-years from the galactic center, not at the edge, not at the core. Out in the suburbs, in a minor spiral arm called the Orion Spur, a small branch extending off the larger Sagittarius arm, we are not central, we are not special. We are in a quiet neighborhood, far from the action. The galactic center itself is a dense, violent place, a supermassive black hole called Sagittarius A, weighing roughly 4 million times the Sun's mass, surrounded by densely packed stars, radiation, and turbulence. Out here, 26,000 light-years away, things are calmer, darker, lonelier, and we are moving. The Sun orbits the galactic center at approximately 828,000 kilometers per hour, about 230 kilometers per second. At this speed, it takes roughly 230 million years to complete one full orbit around the galaxy, one galactic year. Think about that timescale. The last time the Sun was in this exact position in its orbit, the age of dinosaurs had just begun. Mammals didn't exist yet. The supercontinent Pangaea was still forming. Earth has completed roughly 20 full orbits around the galaxy since it formed 4.5 billion years ago. Human civilization, all of it from the first cities to the present day, is a blink, a rounding error. The Sun has moved only 0.004% of the way around the galaxy since humans invented writing. This is galactic time, deep, slow, indifferent to the frantic scrambling of biological life. Now zoom out further. Imagine looking at the Milky Way from outside, a God's eye view, as if you could hover above the galactic plane and take it all in. You'd see a luminous spiral, arms of blue-white stars curving gracefully outward from a bright central bulge. Beautiful, majestic, and utterly inhospitable to the idea of human significance. Where's Earth? Invisible. Even the Sun is invisible, one grain of sand among hundreds of billions, drowned in the collective glow of its neighbors. If you could somehow tag our solar system with a flashing beacon and watch the galaxy rotate, you'd see that beacon creep along its orbit at an agonizingly slow pace, one full circuit every 230 million years. In a human lifetime, the Sun moves roughly 0.003% of the way around the galaxy. We don't move through the galaxy, we drift. And the Milky Way itself isn't static. It's moving too, pulled by gravity toward the Virgo cluster, falling through the universe at hundreds of kilometers per second. The entire galaxy, all 200 billion stars, all the gas and dust and dark matter holding it together, hurtling through the void like a frisbee thrown into infinite darkness. Yet from Earth, on a clear night, it looks peaceful, a gentle smudge of light. You can barely see it unless you leave the cities behind. Here's the unbearable truth. The Milky Way is incomprehensibly vast, and we occupy an utterly unremarkable position within it. Not at the center, not at the edge, not in a particularly dense region or a particularly empty one, just somewhere. One star among hundreds of billions in a galaxy that doesn't know we exist. And this entire galaxy, this continent-sized ocean of stars, is just one galaxy. There are others, so many others. If the distance to Proxima Centauri broke your intuition, if the 100,000 light-year span of the Milky Way seemed incomprehensible, then brace yourself, because the nearest major galaxy is 2.5 million light-years away, and there are trillions more beyond that. Part 9. Galaxies Beyond Ours. The Milky Way feels like everything. 100,000 light-years of stars, gas, and darkness, our cosmic home, our island in the void. But look up again, that fuzzy patch in the Andromeda constellation, barely visible to the naked eye. That's another galaxy, the Andromeda Galaxy, and it's 2.5 million light-years away, 2.5 million light-years. Light that left Andromeda when early humans were just learning to make stone tools is only reaching Earth now. When you look at Andromeda, you're not seeing it as it is. You're seeing it as it was before our species even existed in its current form. Andromeda is enormous, roughly the same size as the Milky Way, possibly larger. It contains around 1 trillion stars. 1 trillion. If every human on Earth represented one star in Andromeda, we'd still need 140 Earths worth of people to account for them all. And despite containing 1 trillion suns, despite being slightly larger than our own galaxy, Andromeda appears as a faint smudge in the night sky, a ghostly thumbprint barely distinguishable from darkness. Distance doesn't just separate us from Andromeda, it erases it. Even something as vast as a galaxy becomes nearly invisible across millions of light years. But Andromeda isn't alone out there. The Milky Way and Andromeda are part of the local group, a collection of roughly 80 galaxies bound together by gravity, spanning about 10 million light-years. Most of these galaxies are small, dwarf galaxies, satellite galaxies orbiting the Milky Way or Andromeda like moons. Only 3 are truly large spirals: the Milky Way, Andromeda, and Triangulum, 10 million light-years. That's the neighborhood. But zoom out further, much further, and you see that the local group itself is a minor suburb of something vastly larger, the Virgo supercluster. The Virgo supercluster contains at least 100 galaxy groups and clusters, totaling tens of thousands of galaxies spread across roughly 110 million light-years. Our local group sits near the outer edge, again, not central, not important, just one small gathering of galaxies among thousands, drifting in a gravitational dance around the supercluster's center. And this is where the universe reveals its true structure. Galaxies don't scatter randomly through space. They cluster, they form groups, which merge into clusters, which connect into superclusters, which stretch along vast filaments of dark matter like cities connected by highways. These filaments, threads of galaxies spanning hundreds of millions of light years, form the cosmic web. Between the filaments, voids. Not empty space dotted with a few galaxies, voids. Regions hundreds of millions of light years across containing almost nothing. No galaxies, no stars, no light, just darkness and expansion, vast bubbles of emptiness where matter simply isn't. The largest known void, the Bhuta's void, spans roughly 330 million light-years. If you were somehow placed in the center of it, you'd see almost nothing in any direction. A handful of galaxies scattered through an ocean of darkness. No Milky Way, no Andromeda, no reference points, just void. This is the architecture of the universe. Vast interconnected filaments of galaxies surrounding incomprehensible voids. Structure on a scale that makes galaxies, those continent-sized collections of billions of stars, look like grains of sand scattered along cosmic threads. And we're still not done zooming out, because the Virgo supercluster, immense as it is itself part of an even larger structure, the Laniakea supercluster, a gravitational basin containing roughly 100,000 galaxies spread across 520 million light-years. 520 million light-years. Every galaxy in Laniakea is being pulled toward the same gravitational center, the Great Attractor, a region of space so dense and massive it tugs on everything within hundreds of millions of light-years. The Milky Way, Andromeda, Virgo, all of it, falling slowly toward this invisible anchor over timescales measured in billions of years. And even Laniakea isn't unique. It's one supercluster among many, separated by voids, connected by filaments, part of a web that extends as far as we can see. How far can we see? The observable universe spans roughly 93 billion light-years across. It contains an estimated 2 trillion galaxies. 2 trillion, each one a Milky Way, each one containing billions or trillions of stars. Each one separated from its neighbors by gulfs of space so vast that light takes millions or billions of years to cross them. The Milky Way, our home, our galaxy, our 100,000 light-year island of stars, is one galaxy among 2 trillion. And Earth is one planet, orbiting one star, in one galaxy, in one local group, in one supercluster, in one filament of the cosmic web. We are so small that the metaphor of a grain of sand fails. We're smaller than that. We're a bacterium on a grain of sand, on a beach, on a continent, on a planet made entirely of beaches. We've been measuring smallness in distance, kilometers, light years. Distances so vast they break comprehension. But there's another dimension to our insignificance, one that's even more humbling. Time. The universe is approximately 13.8 billion years old. Earth is 4.5 billion years old. That means Earth didn't exist for the first 9.3 billion years of cosmic history, roughly two-thirds of the universe's entire existence. For billions of years, the cosmos spun on without us. Stars were born, lived, and died. Galaxies collided and merged. Black holes devoured matter. The universe expanded, cooled, and evolved. All of this happened before our planet even formed. We are not ancient. We are recent. Let's compress this timeline to something more intuitive. If the universe's 13.8 billion years were condensed into a single calendar year, January 1st, at midnight representing the Big Bang, Earth wouldn't form until September 2nd. Life wouldn't appear until late September. Multicellular life? Mid-November. Dinosaurs? Christmas week. They'd go extinct on December 30th. And humans? Modern Homo sapiens would appear at 11:48 p.m. on December 31st, 12 minutes before midnight. All of recorded human history, everything from the first cities to the present day, would unfold in the final 14 seconds of the year. 14 seconds. The Roman Empire? Risen and fallen in 2 seconds. The Renaissance? A blink. The Industrial Revolution? A fraction of a second. Your entire life? An immeasurably small sliver of the final second. This is what time does to our significance. It compresses us into irrelevance. Now consider the stars. Many of the stars you see in the night sky are older than Earth. Red dwarfs, the most common type of star, can burn for trillions of years, thousands of times longer than the current age of the universe. Some of these stars will still be shining long after our sun has died, after Earth has been vaporized or frozen into darkness, after every trace of human existence has vanished. The sun itself has roughly 5 billion years left before it expands into a red giant, engulfs the inner planets, and eventually collapses into a white dwarf. Earth will be gone by then, either incinerated or flung into a different orbit. Life as we know it will end billions of years before the sun's final death. 5 billion years sounds like forever. It isn't. In cosmic terms, the sun is middle-aged, ordinary, not particularly long-lived. Red dwarfs will outlast it by factors of hundreds or thousands. The universe itself will continue expanding for trillions upon trillions of years, possibly forever, long after the last stars have burned out and the cosmos has faded into cold, dark silence. Humanity's entire existence, past, present, and conceivable future, is a flash, a spark in the night, one brief moment of warmth before the universe moves on without us. And it's not just us. All civilizations, if they exist, are likely flashes. Even if intelligent life arises on millions of planets across the galaxy, even if some civilizations endure for millions of years, they're still temporary. Stars die. Planets become uninhabitable. Galaxies drift apart. The conditions that allow for complexity, consciousness, and civilization are fragile and fleeting. We exist in a narrow window of cosmic history after the universe cooled enough to form stable structures, but before entropy grinds everything to silence. This window may last trillions of years, but it's still temporary. Eventually, star formation will cease. Black holes will evaporate. Even protons may decay, dissolving matter itself into radiation. The universe is not permanent. Neither are we. This temporal smallness cuts deeper than spatial smallness. You can imagine traveling across space, theoretically reaching other stars or galaxies given enough time and technology. But you cannot escape time. You cannot outlast the universe. You are trapped in your moment, a firefly flickering briefly in an incomprehensibly long night. 14 seconds on the cosmic calendar. That's all we get. Every empire that has ever risen, every book ever written, every symphony composed, every equation solved, every act of love or cruelty or brilliance. 14 seconds. And yet, paradoxically, this is also liberating, because if we're this small, this temporally and spatially insignificant, then our mistakes don't matter cosmically. Our failures aren't permanent. The universe will not remember us, will not judge us, will not care. But neither will it remember our triumphs. We are small in space, we are small in time. And now, in the final section, we must ask, what does this smallness mean? So here we are. We've traveled from Earth, our seemingly infinite home, through the solar system, past neighboring stars, across the Milky Way, out into the cosmic web of galaxies, filaments, and voids. We've watched ourselves shrink from the center of everything to a speck on a speck, orbiting a speck, in a galaxy that is itself a speck among trillions. We are unimaginably, almost absurdly small. But does that make us insignificant? Here's the thing about size. It doesn't grant meaning. The universe is vast, yes, but it's also mostly empty, mostly dark, and as far as we can tell, mostly dead. Hydrogen clouds don't contemplate their existence. Black holes don't write poetry. Galaxies don't fall in love. You do. Consciousness, awareness, thought, the ability to look up at the stars and ask why, appears to be extraordinarily rare. We found no evidence of it anywhere beyond Earth. Maybe it exists elsewhere. Maybe the galaxy is teeming with civilizations we simply haven't detected. Or maybe we're alone, a singular spark of awareness in an otherwise indifferent cosmos. Either way, you are rare. A star is large, but it doesn't know it's large. It burns through its fuel mindlessly, following physics, incapable of wonder or reflection. You are small, but you know you're small. You can comprehend the vastness that dwarfs you. You can measure it, map it, feel awe in its presence. That capacity to understand your own smallness is itself extraordinary. This isn't an argument for human supremacy or cosmic specialness. We are not the center of the universe. We are not protected or favored by the cosmos. The universe operates according to physical laws that care nothing for our survival or happiness. Stars will explode, planets will freeze, black holes will evaporate, humanity will end, and the universe will continue as if we never existed. But meaning isn't something the universe grants, it's something you create. Every act of kindness, every moment of beauty, every discovery, every connection, every fleeting experience of joy or love or wonder, these things matter because you decide they matter. Not because the cosmos endorses them, but because you are here now, capable of experiencing them. Smallness, in this sense, is liberating. You are not burdened with cosmic significance. The universe doesn't demand that you justify your existence on a galactic scale. You don't need to matter to Andromeda. You don't need Neptune to care about your choices. You matter to yourself, to the people around you, to the small fragile sphere of experience you inhabit. And that's enough. The philosopher Blaise Pascal wrote, "Man is only a reed, the weakest in nature, but he is a thinking reed." He was right. We are fragile, temporary, vanishingly small, a cosmic accident on an unremarkable planet. But we are also the part of the universe that woke up. We've crossed galactic distances. We've seen superclusters and voids. We've grasped barely the scale of cosmic structure. But now we need to confront something even more unsettling. We can't see the whole universe. Not because our telescopes aren't powerful enough, though that's part of it. We can't see the whole universe because the universe itself won't let us. There's a horizon, a fundamental limit beyond which light simply hasn't had time to reach us. Let's start with the constraint, the speed of light. Light travels at 300,000 kilometers per second, roughly 9.5 trillion kilometers per year. This is the fastest speed at which information can travel through the universe. Nothing with mass can reach it. Nothing can exceed it. It's a cosmic speed limit built into the fabric of space-time itself. The universe is approximately 13.8 billion years old. You might think, then, that the observable universe, the region of space from which light has had time to reach us, would be 13.8 billion light-years in radius. But you'd be wrong, because the universe isn't static, it's expanding. Space itself, the actual fabric of the cosmos, is stretching. Galaxies aren't just moving through space away from each other, the space between them is growing. And this expansion has been happening since the Big Bang, accelerating over time. Here's what this means. While light from a distant galaxy has been traveling toward us for billions of years, the galaxy itself has been moving away from us as space expands. By the time that light reaches Earth, the galaxy is now much farther away than it was when the light was emitted. The result? The observable universe has a radius of roughly 46.5 billion light-years, giving it a total diameter of about 93 billion light-years. 93 billion light-years. If the Milky Way were the size of a grain of sand, the observable universe would be a sphere roughly 150 kilometers across, bigger than a large city. And the Milky Way, our entire galaxy, with its hundreds of billions of stars, would still be just one grain of sand among billions scattered throughout that volume. But here's the deeper implication. When you look out into space, you're not seeing the universe as it is now, you're seeing the universe as it was. Look at the Sun, and you see it as it was 8 minutes ago. Look at Proxima Centauri, and you see it as it was 4.2 years ago. Look at Andromeda, and you see it as it was 2.5 million years ago, before modern humans existed. The farther you look, the further back in time you see. The most distant galaxies we've detected are over 13 billion light-years away. We're seeing them as they were just a few hundred million years after the Big Bang, ancient primordial galaxies that may not even exist anymore in their current form. They might have collided with other galaxies. They might have been torn apart by gravitational forces. They might have evolved into something completely different. We'll never know, because the light showing us what they've become won't reach us for billions of years. There is no now in the universe. There is no universal present moment where we can see everything as it currently exists. The universe is a patchwork of different times, nearby objects seen in the recent past, distant objects seen in the ancient past, all layered together into a single view. And beyond the observable horizon, beyond that 46.5 billion light-year radius, more universe, almost certainly. The observable universe is just the region of space from which light has had time to reach us. But space doesn't end at that boundary. The universe likely extends far beyond what we can see, possibly infinitely. There could be galaxies out there, trillions of them, whose light will never reach us, not because the light is too faint, but because the expansion of space is carrying them away faster than light can travel toward us. They are receding beyond our cosmic horizon, forever unreachable, forever invisible. In fact, due to the accelerating expansion of the universe driven by something we call dark energy, but don't truly understand, galaxies that we can currently see will eventually disappear from view. Billions of years from now, distant galaxies will redshift into invisibility, their light stretched into wavelengths too long to detect, as space itself pulls them beyond the observable horizon. The universe is not only vast, it's getting more vast, and as it expands, it's hiding itself from us, piece by piece, galaxy by galaxy. This is the ultimate isolation, trapped not just by distance, but by the structure of space-time itself. We live in a bubble 93 billion light-years wide, surrounded by a universe we can never see, never reach, and never know. And even this bubble, vast as it is, may be just a tiny fraction of the whole. Some cosmological models suggest the universe is infinite. Others suggest it's finite but unimaginably larger than the observable portion, perhaps millions or billions of times bigger. We don't know. We may never know. What we do know is this: The 2 trillion galaxies in the observable universe, each containing billions or trillions of stars, may represent only a small sample of what actually exists. Everything we've discussed, the Milky Way, Andromeda, the Virgo supercluster, the cosmic web, the voids, all of it confined to a sphere 93 billion light-years across. And that sphere might be a drop in an infinite ocean. We are small in the observable universe. We may be incomprehensibly smaller in the actual universe, but we're not done yet. Because even time itself conspires to make us smaller still. Let's come back home. You are standing on Earth, a rocky planet 12,742 kilometers across, orbiting an ordinary yellow star at a distance of 150 million kilometers. Your star is one of roughly 200 to 400 billion in the Milky Way galaxy, a barred spiral structure, 100,000 light-years wide, located in a quiet suburban arm far from the galactic center. The Milky Way is one galaxy in the local group, which is one small cluster in the Virgo supercluster, which is one structure in the Laniakea supercluster, which is one node in the cosmic web stretching across the observable universe, a sphere 93 billion light-years in diameter, containing an estimated 2 trillion galaxies. And the observable universe may be only a fraction, perhaps an infinitesimal fraction, of what actually exists. You are here, on this planet, in this moment. A collection of atoms briefly arranged into consciousness, standing on a thin shell of rock and water, surrounded by an impossibly thin layer of breathable air, hurtling through space at hundreds of kilometers per second on a journey around a galaxy that will take 230 million years to complete. You occupy 14 seconds on the cosmic calendar. You are smaller than a bacterium on a grain of sand on an infinite beach. And yet, you know this, you can hold the entire structure of the cosmos in your mind, not perfectly, not completely, but enough to grasp the outline, enough to feel the weight of it, enough to look up at the stars and understand, truly understand, that you are seeing ancient light from distant suns, that space is vast beyond comprehension, that time is deep beyond imagination. A hydrogen atom in a distant nebula doesn't know it exists. A galaxy spinning through the void has no awareness of its own grandeur. But you, fragile, temporary, impossibly small, can comprehend them both. In you, the universe has developed eyes. It has grown a nervous system. It has become capable of looking back at itself and asking, what am I? Where am I? How did I come to be? This is not an accident of chemistry. Or perhaps it is, but if so, it's the most extraordinary accident imaginable. You are made of star stuff, as Carl Sagan famously said. The iron in your blood, the calcium in your bones, the oxygen in your lungs, all of it forged in the cores of ancient stars that exploded billions of years ago, scattering their remnants into space, eventually coalescing into planets, into oceans, into life, into you. You are the universe experiencing itself, locally, briefly, imperfectly, but genuinely. The cosmos is vast. You are tiny. And somehow, against all probability, you are here, aware, thinking, capable of wonder and love and curiosity and awe. The universe doesn't care that you exist, but you care. And in a cosmos defined by entropy, indifference, and the slow march toward heat death, the fact that anything can care at all is remarkable. So, yes, you are small, smaller than you ever imagined, smaller than language can properly convey. A mote of dust in an ocean of darkness clinging to a cooling rock, alive for just a moment, in a universe that will continue for trillions of years after you're gone. But you are not insignificant. You are the part that woke up. And for now, for this brief, improbable moment, that is enough. You are here, small, but aware.